But I'm surprised no one has questions. What?
So I'll probably have some later. Right now.
All right. And who started the homework? I know you did. You got a head start on it. You did too.
I only did one problem.
All right. Which
I
problem?
did I think it was problem 3.
Okay.
It was the one with the 50 pips.
Mm-hmm.
And the 3.
Mm-hmm.
Yeah. I was gonna do number 1.
Yeah.
I don't know if we did that one yet in class.
Number 1.
Yeah.
That's composite, right?
I don't understand number 1 either.
Which one's number 1?
I don't know, it was like, I know number 2 we did something like that in class.
Let's see. Homework 1. Problem 1. It's homework 5, right?
Yeah. Yeah, that one.
Ah, it's a composite. It's the same method, but it's just 2 materials, steel and concrete.
It looks like get out of jail, but you just multiply it.
Well, I was thinking that. I was thinking it was like the redwood that we did.
Yeah, the area of the steel for this would just be the area of the reinforcing bars, which, what's the area of a number 8 reinforcing bar? Who here can tell me?
1 inch.
Is it 1 inch?
Just get number 8.
Yeah.
No, that's the diameter. I said the area.
Oh yeah.
It's 0.79 square inches per bar, pi over 4.
So
Yeah, it's the area equation times the bar number divided by 8. Most times. Once you get to number 10, then you can't really apply that rule because the 10 over 8 is not equal to 1.27. And that's the size of a number 10 bar, right? 10 over 8, yeah. It's off by 0.02 inches. But yeah, the area of the number 8 bars is just going to be 8 times 0.79. And then the area of the concrete is just going to be the gross cross-sectional area of the concrete minus the area of the steel. And then from there, you just solve the problem like everything else. Make sense?
yeah.
All right. But moving away from homework and moving towards something new, we are talking about a very fun topic. This is one of my favorite topics, but many of you will probably hate it. It is the transformation of stresses. Now, the best way to explain what this is let's consider we have an axial bar, just like that, and it has a support at the end, so it's fixed, and it's subjected to a force of, I don't know, let's say 25 kips. Right? Now, in a traditional sense, if we were designing this, let's say we know that the stress, if we wanted to compute it, would equal what? Let me just actually, instead of writing 25 kips, I'm just going to define it as just some arbitrary force, P. And then it has some arbitrary cross-sectional area, A. So from a traditional sense, we know that the stress in the bar is equal to force divided by area, right? Everyone agrees with me on that? Good. Now, how do you guys think it'll fail? You guys think it'll just rip out of the wall probably, right? Or maybe it'll just snap at some point in the middle. Either way, it's going to yield, right? Good. Now, let's say that instead of it just yielding or being pulled out of the wall, let's say that we've got some type of weld line here. right? Where do you guys think it would fail at that point? Along the weld line. So then what would the stresses along the weld line be? Is it just P over A?
It would be, like, it would be along that same, like, the angle.
Yeah. But here's the thing. How many stresses are going to be present along that line? Is it just one stress, the axial stress? Is it 2 stresses, 3 stresses? What do you guys think?
At least 2.
At least 2. What are the 2 stresses?
I mean, I'm sure there has to be some type of vertical stress going up and down and going left and right. Because like if it's slanted right and it's pulling, it's going to want to shear off below.
Exactly. So if we were to look at this from like a side perspective here, let me just re-sketch this really quickly. And then let me just take the small eraser. And then I am just going to use this line here. Right? What we're going to have is just as we're going to have a normal stress. We generally call this stress sigma. So this is just the normal stress along the plane. And then just like Joe said, we're going to have a shear stress develop. So we have 2 stresses developed, even though there's only one load being applied here. Now, it's important to note that this weld line, we need to know what this angle is. This angle being some angle theta. And so when we do the calculations, all right, I'm not going to show you guys the full derivation behind everything because I know you guys don't really give a crap. But this normal stress or the transformed stress, if you guys want, you can call this sigma t and tau t. This transformed stress is equal to the initial stress, sigma, times cosine squared theta. And then this transformed shear stress is going to equal the normal stress multiplied by sine of theta times cosine of theta. Take my word for those equations, all right? There's a lot of math that goes into solving those, but just take my word. Now, one thing you guys will note is this is explicitly for a case of uniaxial loading. Let me actually move this up here. Right. So let's say that the force P was equal to that 25 kips that we said. And then the weld line theta we said was, I don't know, 45-degree angle. What would the stresses along the weld line have to be? Can somebody compute that for me real quick? You guys need the area, which we'll say, just to be nice, 1 square inch. 12.5 for what?
Is that,
For which stress?
well, the bottom one?
The shear stress?
Yeah.
Yep, I get 12.5 KSI. Who here got the normal stress, the normal transformed stress? What'd you get, Olivia? Yeah. And that's because when the cosine of 45 and sine of 45 are the same thing. So that comes from unit circle principle, if you guys remember that from algebra. But now let's say that we wanted the angle to be, I don't know, let's say this is at a 60-degree angle. No, 30-degree angle. What do you guys get then? What do you get?
18.75 for the top one, and then 10.83 for the bottom.
And then what about theta equals 0 degrees? What do you guys get for that? I'm just going to tabulate these. This would be somebody else. Yes.
Would it be 25 for the top and 0 for the bottom?
Yes. And the reason for that is because then technically the weld is just parallel to the cross section. So then you would just need to design the weld for the full axial load. Does that make sense? Great. And that's pretty much stress transformations. Now, the reason we might do this is we might have to weld two materials together. Sometimes in like reinforced concrete design. We actually consider it in the design. And see? And that's a horrible picture. Come on. Here we go. You guys can kind of see the crack development. How does it fail? You see where all of the cracks are developing? Well, it's going to fail along those crack lines. So it's important to understand what the stresses are along those crack planes. So for example, towards the middle of a beam subjected to flexure, most of the failure is going to be occurring at the bottom because it's just going to be splitting right down the middle because of extreme tension at the bottom, right? But along the edges of the beam, those are shear failure cracks. which for concrete specifically actually generally fails roughly at around a 45-degree inclined plane. So because of that, you would generally design for the shear and normal stresses along those inclined planes. Does that make sense? Good. Whoops, wrong one. Where's my thing? All right. Now we can complicate things a bit more since you guys fully understand how stress transformations work. Now let's say we just have an arbitrary block. This can be any block. It could be steel, it could be wood, doesn't matter. But now let's say that this block is subjected to a stress in the y direction, a stress in the x direction, and then a shear stress, just like that. And then it'll have associated counterpart stresses just to satisfy equilibrium, which this would just be, whoops, let me drag this out a bit. This would be like sigma x, this would be sigma y, and then this would be tau xy. All right. Now this, I'm going to say, is the positive sign convention for 2D stresses. All right. And so if we were to look at the stresses for any particular orientation, we can compute the stresses by transforming this little block. So for example, if instead, I'm actually gonna erase these lines here just because I think I could come up with something a little better. What I want to do instead is just draw out something really quickly. So we could have like a beam here. With some force. And so what this block is really supposed to represent is like this really microscopic point that could be anywhere along there. So this could just be some arbitrary stress block. So it's really small, so don't mind its size. It's just supposed to be some point within our beam that's supposed to be infinitely small. And for our beam, we should generally know what the normal and shear stresses are within that beam. So if we wanted to determine the stresses along any particular orientation, for example, we can determine what the stresses are by rotating the plane as such and compute transformed stresses. And then we would have equivalent counterparts. Let's call this our plane here for reference, an X and Y plane. And then I'm not going to be able to rotate that. We could call that theta. This we can call x prime and y prime. Actually, call them xt and yt to represent the transformation that we're interested in. And then from here, we can call these sigma xt, sigma yt, and then tau xy t. T representing the transformed stresses for some rotated block. This is basically doing the same thing that we did above for the weld, but now we're applying it into a more universal case scenario. Does that make sense? So, when we look at these stress equations, we can use equilibrium to find the transformed stresses. Now, I'm not going to do equilibrium for this because the entire process is horrendous, but we will get the following equations. These equations are kind of long, and I recommend you guys putting them on your flashcards. All right? So, our transformed stress for sigma t, xt I mean, is going to equal sigma x plus sigma y divided by 2 plus sigma x minus sigma y divided by 2 times cosine of 2 times theta plus tau xy sine of 2 theta. It is a very long equation, right? Fortunately, with many of these problems, they are just generally plug and chug. Now, for sigma yt, we are going to have basically the same equation, except it's going to have a minus sign instead of those plus signs. Everyone follow so far? I'll give you guys a minute to write down the rest. Let me know when you guys are ready to proceed. Oh, whoops. I had just said they're minus signs. If you guys didn't notice, that should be a minus sign too, in case you guys wrote that incorrectly. Just raise your hand when you're ready to proceed. I want to make sure that everyone has the equations written. I think Nicole and Christian are still writing, and Edgar. All right. Now there's one more equation, and it is the transformed shear stress equation, which is just going to equal negative sigma x minus sigma y divided by 2 sine of 2 theta plus tau xy cosine of 2 theta. Now, one thing that should be noted is sigma x and sigma y and tau xy are from the original loading, from the original untransformed section. Does that make sense? And just a little side note, as long as you do everything correctly, you can check your answers by adding sigma x transformed plus sigma y transformed. And those should technically equal the original stresses of sigma x plus sigma y. So that's like a good little trick to remember just to make sure that you're plugging in your answers correctly. Are there any questions about these equations at all? I'll go into more detail next class because next class I show you guys how to draw these for an infinite amount of angles using a circle. And I think that solving the problems using the circle is actually a lot easier, but I want you guys to know these equations also. Just so you have two methods of determining. All right. Now, the best way of doing this now is just going straight into an example. And one of my favorite problems is involving soil mechanics. Has anybody ever heard of a uniaxial compression test for soil? No one? Here, let me pull it up just so you guys can see. Yeah, it's a UCS test. They prepare the sample and then it's used to get geotechnical data. Let's see. Which is generally important for if you're designing something like retaining walls, for example. So there's no load applied right now. They're just finishing up setting up this equipment. Come on, get your fat hand out of the way. There we go. And so it just applies a really small load. And it's just a constant pressure pushing downwards. But pay attention to how the soil fails. I don't know why they're zooming in on anything, but. More and more load. Wow, we would have been here all day. Failure of the specimen looks like it's starting to occur. And if you guys take a really close look at the soil, you guys should see some type of crack development begin to develop within the soil sample. And again, they moved the camera. But hopefully you guys see the crack develop within the soil. Now, is that perpendicular to where the load is applied, or is it applied at an angle? You guys will notice it's just being applied as an angle. And by this point, the test is done. You guys are probably like really bored with the fact that it's soil, but I love soil mechanics. This is how your footings are designed, and foundation systems, and retaining walls. It's fun. So, for this soil problem that I'm going to give you guys, we have a soil sample, whoops, that fails at an inclined angle. And we're going to say that this angle, theta, is equal to 45 degrees. Now, instead of giving you guys an axial load, it's applied uniformly at the top with sigma, with a vertical stress of 57 kilonewtons per meter squared. Let me indicate that this is the failure plane. Right? So, using our stress equations, what I want to know is what is our transformed stress for X, transformed stress in Y, and the transformed shear stress, just using the equations. And I'll give you guys a little hint here. We've got sigma X is equal to something, sigma Y equals something, and tau xy is equal to something. What is the applied stress in the X direction? It's 0. What is the applied stress in the Y direction?
57 kilonewtons per meter squared.
Positive or negative?
Negative.
Negative. Keep track of the signs. And then the applied shear stress? Is there an applied shear stress on this problem? The answer is no. All right, so we're just really quickly using the transform stress equations. Just plug and chug the answers and let me know what you guys get. Who here's got all the stresses? What did you get?
-28.5,
For which ones?
all of them.
Yep. Who here didn't get negative 28.5? You didn't?
I got it for the last one, but I think we may have plugged in wrong for the first two, but for the first two, I got 0 for both.
You got 0 for both?
Yeah, and then the 28.5.
Okay. How did you plug it in for the first two?
I think it's because I was doing it separately rather than all of it together. Like I was doing the 0 plus the -57 and then dividing by 2 and then also doing the other one and then adding those two together and then doing the cosine.
What did you plug in for the cosine?
For the cosine is I would do the cosine button, the 2 and then the 40 parentheses 45.
You did 2 times 45? Okay.
I think I just plugged it in wrong. Just for the last one I got the 20.
Yeah. So when you're solving for these, your equation should basically look something like this. Oops, that does not look nice. And this should have given you negative 28.5 kilonewtons per square meter. And then sigma yt is just going to be the same thing, but instead of a plus, it's going to be minus, which is going to give you, again, the same thing, negative 28.5 kilonewtons per square meter. This is just going to equal 0 because cosine of 90 degrees is 0. And then for tau xyt, you get negative 0 minus 57, negative 57, sorry. Let me rewrite this. Sine of 2 times 45 plus 0. And this gives you negative 28.5 kilonewtons per square meter. Make sense? All right. And so if we were to look at this from a perspective of the failure plane, where's my line tool? Here it is. Then our stresses end up basically being a vertical compression stress of negative 28.5 kilonewtons per meter squared, and then a shear stress of negative 28.5 kilonewtons per meter squared. Make sense to everyone? Good. All right. Now, I have another example for you guys. This time we're going to be dealing with a more complicated loading with a 1 kip per square foot stress. A shear stress of 2 kips per square foot. And 3 KSF. All right. Firstly, what is sigma x, sigma y, and tau xy equal to?
What's the plan for this?
the axes are just x and y. And those are both positive.
So then, sigma x would just be, 3 KSF, right?
Sigma x is 3 KSF, positive or negative?
Positive.
Yep. What about sigma y?
-1 KSF.
Yep. Now here's a tricky one. What about tau xy?
You just like add them or something?
Not quite. No, they're all the same shear force. Yeah.
Would it be two?
Nope.
No?
Positive or negative 2?
Positive?
Nope.
Negative?
It's -2. All right. This was a trick. I told you guys the positive sign convention looked like this. Anything that does not look like the shear stress is going to the right and up, or down and left here, is negative. Another way of thinking of it is, let's look at the plane. This is moving downwards. So that would be a negative sign, right? And then this one's moving to the right? So is that a positive or a negative sign? Now, if you were to multiply a negative and a positive, what do you get? So that's another way of doing it. And then it works for this way also, right? It's moving to the left. So it would just be negative here. And then it's moving up, which is positive, which again gives you a negative value. All right. So what I want you guys to do now is find the transformed stresses and if we rotated this thing negative 22.5 degrees. You get it, Christian?
Yep.
What'd you get?
For x, I got 3.83, y, negative 1.83, and x, y, 0.
Tau x, y, 0. Who here gets that also?
I only got XT so far.
What?
I only got XT so far.
All right. I'll give you guys a few more moments. So Christian, using the equations, 3.83 KSF, negative 1.83 KSF, and then 0 KSF. Doesn't mean these are correct, so I want everybody to do it. What was that, Joe? Are you throwing shade?
No, you were throwing shade.
I'm throwing shade.
Yeah, that's fine.
So have I convinced anyone to go into engineering yet?
No.
No? This stuff is used, this stuff that I'm teaching you guys right now is the stuff that computer software uses to analyze structures.
See, why would I use using computer software?
Because if you don't interpret the computer software results properly, then
I think that class would be more useful than this, no?
you don't get taught software. You need to know how it works, right? Like if I showed you the math behind how the software works, like it would cripple my hands. Because you would need to solve like systems of equations of like 10 by 10 unknowns simultaneously. Did everyone get these stresses? 3.83, negative 1.83, and 0? If you didn't, let me know. Raise your hand if you didn't.
I think it's just a calculator.
Well, let me come over to you. Let's see. There could be some around, but if you're like far off.
I think the calculator is more efficient. I think it's time to retire the calculator.
You're in degree mode. I'll write it out.
Do that, I tried writing it out first before I put it in, because.
I'm sure it's probably written out correctly. It's just I can't see it. The calculators, I can never tell with
I
calculators.
wrote it down on my paper too, just so I put it in.
All right. So for this, you should have gotten 3 plus negative 1 divided by 2 plus 3 minus negative 1 divided by 2 cosine of 2 times negative 22.5 plus negative 2 sine of 2 times negative 22.5. Did everyone get that? Or am I wrong anywhere? That's what you got? And you got these answers also on the left-hand side? All right. Now for this, it would just be the same thing, except using the subtraction symbols. Right? So that's a nice little trick, is just copy the equation from above, just replace the pluses with minuses. And then for this one, what you should have gotten is negative 3 minus negative 1 divided by 2 sine of 2 times negative 22.5 plus negative 2 cosine of 2 times negative 22.5. All right. Now, what do you guys notice about the stress? About these stresses here? Sigma xt, sigma yt, tau xyt. What do you guys notice? There's a reason why I chose negative 22.5 degrees for this. Any takers? Nobody wants to take a crack at it? No one? I'm disappointed. What do you guys notice about the shear stress? 0. There's no shear stress within this angle if you rotate it. So if you guys were to rotate this thing, this thing isn't going to be a perfect rotation because I don't think I can rotate this. Yeah, no. Oh, yikes. Stroke eraser. So if I were to try and just sketch this out using a 22.5 degree rotation, excuse my horrible drawing while I try and draw this because I can't apparently rotate a rectangle. Hold on, what am I doing? This is like definitely not 22.5 degrees. It would be more like this. Where our initial rotation, I'm going to draw just like this, of X and Y, has now become something more like YT and XT, with this angle here being negative 22.5 degrees. All right? And so the stresses acting on these planes are 3.83 KSF, and then negative 1.83 KSF with no shear. I'm just going to move this down to here. The reason why this is important is because of the fact that there is no shear stress. And when we have a state like this, when tau xy t is equal to 0, it means that sigma xt and sigma yt, let me not write an equal sign, are equal to what we call principal stresses. And what these principal stresses are, is they are the maximum and minimum axial stresses. So this means that if you're designing a member for axial compression, these are the stresses you want to use. Not 1 KSI, not the 3 KSI. You want to be using the negative 1.83 and the 3.83 when you're designing for tension and compression, respectively. Does that make sense? Because then if you're designing for 1 KSF and 3 KSF, you're neglecting 0.83 KSF in tension and compression for each one, right? Which means it'll fail along this particular plane. And what's significant about this negative 22.5 is that it's equal to the principal stress plane. Note that it's not always 22.5 or negative 22.5, I mean. It just happens to be negative 22.5 for these loads here. Now you can derive an expression to determine what the angle of rotation needs to be for the principal stresses to be calculated. And that equation is going to be written as such. We call theta the principal stresses, stress plane, theta P, which is the angle from the original loading at which the principal stresses occur, so it's how much you need to rotate it by, is equal to 1/2 times the inverse tangent of 2 tau xy over sigma x minus sigma y. Similarly, you can just rewrite it as such. Tangent of 2 theta p is equal to 2 tau xy over sigma x minus sigma y. And this is, in case you're curious, this comes from a derivation of this equation here. No, it comes from a derivation of this equation here, where you would just let this equal 0. And then you could just solve for theta outright, in which case then you would find the expressions that you need. Does that make sense? I'm not going to walk through it, but that's just for your own guys' sake. So are there any questions about this at all, the principal stresses, and how they are the maximum and minimum stresses? Now, just before our break, the principal stresses are denoted using sigma 1 and sigma 3, where sigma 1 is the maximum value and then sigma 3 is the minimum value. So in this case, sigma 1 would have been the 3.83 KSF, and sigma 3 is the negative 1.83 KSF. And just a quick note, let's say you had sigma 1 is equal to, not sigma 1, but let's say you had principal stresses of negative 4 KSF and negative 10 KSF. Which one do you guys think would be sigma 1 and sigma 3? Which one's greater, negative 4 or negative 10? Which one's the maximum? Negative 4. So negative 4 is your principal 1 stress, sigma 1. and -10 is your principal stress sigma 3. Think of it like this. If you were to plot it along the x-axis, right, sigma 1 is always going to be on the right-hand side of sigma 3. Think of it like that, all right? All right, I'll let you guys take a break. Let's come back in about another 5 minutes, and yeah, 7:15. You guys like this topic?
It's not bad.
No. I'm
You know, I have to ask, always have to ask you a question. So I know you sent it to me, but I'm still kind of confused about it. Like, should I just start this over?
No, you're along the right track.
Okay.
So you know that for the steel, it's going to be both equal to each other, right?
Yeah.
And so you did 2 PST plus PA1, or P aluminum, I mean, and you know that that's equal to 50 kips. So what you just need to do is, what do you want to solve for, the steel or the aluminum?
Should I solve for the aluminum? It doesn't matter.
No, as long as you do it right, you should get the answer regardless. But what do you want to do?
I'll do what's the easier option?
I mean, there's no easier option.
Aluminum then?
Fortunately. All right. So all you need to do is find out how the stress of the steel and the aluminum relate. So how much more force is the steel going to attract than the aluminum? So just do the proportion. What is this entire thing times PST, and then what is this entire thing times PAL?
I have to multiply this by PAL.
Yeah, I mean,
Oh,
here.
wait, I think I remember this now. So I do it like that, and then I write this equation again?
I mean, we could just do it like this. So
Okay.
you've got 40 divided by 1 times 29,000. So that's PST over 725. So you could just write that.
PST over
725.
725.
Yeah.
Okay.
All right. And then we've got 60 divided by 1.5 times 10,000. And we set this whole thing equal to PAL over 250.
Okay.
All right?
But then we have the two unknowns.
Right. But here's the thing. We know how they relate to each other here. So you could just use this relationship between the two to then solve for the equilibrium. And then that's how you get the value.
And then how do I do that, though?
Well, here,
Right.
take the aluminum. All right. Let's say we want to replace the aluminum with its equivalent amount of steel. All right. So take that 250 and multiply both sides by it. So then the steel is just going to be 250 divided by 725. So it's just 10 over 29 PST is equal to PAL.
Wait, so from here, sorry, sometimes it takes me a sec to understand when there are a bunch of variables. I'm multiplying the 250 here, I'm replacing this with this, so it looks like PST over 725 equals
And multiplied by 250
multiplied by 250.
is equal to PAL.
Oh, now I understand.
Yeah.
Now that I wrote it like that.
Right? And so then you get, once you plug in 250 over 725, that PAL is roughly 0.345 PST, or 10 over 29 if you like working with fractions.
Okay.
PST.
Okay, yes.
Mm-hmm. Great. Now what's important about this is the fact that now you can take this value of PAL here and just replace PAL with 0.344 PST.
Okay. So then I just put it up here.
Yeah.
Okay.
So then your equation would be 2 PST plus 0.344 PST, right?
Oh, yeah, okay. And then I just solve this.
Exactly.
Okay,
And that's equal to 50, and then you only have one unknown.
okay, thank you so much. And then it'll be the same for this one. Okay, thank you.
Yep.
I have a question.
Sure. I'm eating my protein bar. Hope you don't mind. I get hungry.
Is that, let's start with the homework.
Failed. I'm kidding.
For number 2, is that similar? I saw the shirt.
Mm-hmm.
Like, I know number 2, they use temperature instead of just, so like, for this, because I know we did one where it was just 1, but like, is it similar to just this, basically?
Oh, did I give you guys both temperature and change and force for problem 2?
There was a lot.
It's this, but the additional this. That's why I was confused.
Let me
Like,
check that. Because if I gave you guys that, that's the hardest problem I think I've given you guys.
That's why,
today.
like, because I'm looking at it, I'm like, I know we did.
Oh yeah, yeah. Mm-hmm. Oh wow, I gave you guys a fun problem to work on.
Yeah, I don't know really where to start besides internal.
It's the summation of the deformations.
Is that gonna be on the test?
It can be.
That entire problem?
Mm-hmm.
Yeah, I'm gonna need more explanation first.
It probably won't be as long because I gave you guys 2 components, so I would probably give you guys 1.
Okay,
So-
good, because that took me a really long.
Unless I gave you guys 2, then that's fine too.
So what do I have to do? So I have to do this and temperature?
Mm-hmm.
Interesting.
All in one problem.
I'll try. Have we ever done a temperature with 2 materials?
You should be able to. It's the same principles.
Is it the same formula
Mm-hmm.
for temperature? Just
Yeah, it's just the only thing
It's
is,
not NLEA. It's.
it would be both. You would need to consider the deformation effects of both the applied force and the temperature change, and then apply the compatibility or apply the reaction force that would balance out both of those combined effects.
Interesting. I might come Thursday for that question.
Okay.
You said our exam is on Thursday?
Next Thursday.
Are we gonna have a review as well?
Tuesday.
Alright, gotcha.
Yeah. Those problems can get really creative because I could have given you guys a statically indeterminate composite member subjected to axial loading and thermal effects, which that probably would have taken you about, that would have been one homework assignment in itself, just giving you guys that. That would take you guys a while, I think. It would take me probably an hour to figure it out.
So it'll take me like 3 hours then.
3 hours? I'm thinking more like 8.
8 is crazy. 8 is insane.
Yeah, that would require you, if you had to do that, that would require you first solving for the statically indeterminate system for computing the stresses, the deformations. But then you would need to find the forces for just this one system. And then for the system 1, what you would need to do then is compute the deformation due to the applied reaction force. And then from there, it's like, all right, then you need to add the 2 results together, which then once you start adding temperature into the effect, yeah, it takes a while. So then what you're really kind of doing at that point is you're solving 4 problems all in one.
So you could just make the test 1 problem then.
Yeah, I can get really creative.
You shouldn't though.
No, the reason I'm not going to is because if you mess up one thing on that problem, I don't feel like looking at everything else without an answer sheet because then I gotta figure out and look heavily in detail at what you guys did wrong and so on and so forth. And that with the way that some of you organize your work is an absolute nightmare. And I don't get paid enough to do that. So I'm just like, just come up with 5 problems entirely unrelated, and there you go.
Thank you.
All right, let's continue. So, another thing that I just really want to add is we went over when the stresses were a maximum, right? The axial stresses were maximum. But what about the maximum shear stress? Right, because that's also going to be a design factor, right? We want to determine what the maximum shear stress in the material is going to be. You guys would agree with me on that, right? Right? So this maximum shear stress, we don't know. We know the principal angle and the principal stresses associated with that angle. Now, when it comes to the maximum shear stress, that's also going to occur at a particular rotation, right? Some orientation on our material. Like if we rotated the block, we would get to some point where only shear stresses occur, right? Do you guys agree with me on that? Because it's all dependent on the angle. So at some point, when you rotate the block, the axial stresses are going to be so small, they're going to be 0, and then your shear stresses are going to be maximum. So for the shear stresses to be maximum, sigma x, sigma x is equal to 0, and sigma y, let me add sigma xt and sigma yt is equal to 0. And then let me add that tau xyt is technically equal to the maximum shear stress. Right. It doesn't mean that sigma x and sigma y were 0. I meant sigma xt and sigma yt. Those transform stresses, they are going to be... Is it 0? No. No, they can't be 0. Oh, right. It's going to equal sigma 1 plus sigma 3 divided by 2. And there's a reason for that. We'll see next class why it is that. All right? But for now, let's assume that we don't exactly know that. One of the things that we do want to note is that the stress, the plane in which the maximum shear stress occurs, we'll call this theta S, plane of maximum shear stress. This is equal to the principal stress plane plus or minus 45 degrees. Another way of writing this is by saying that 2 times theta S is equal to 2 theta P plus or minus 90 degrees. And so by knowing this relationship, this will make more sense next class. Just trust me when I give you guys these equations, because next class there is a visual way of showing you guys how these equations work, and it just makes so much more sense. When you use this equation, you get that tangent of 2 theta s is just equal to sigma x minus sigma y divided by 2 tau xy, which is the same as saying theta s is equal to 1/2 inverse tangent of sigma x minus sigma y divided by 2 tau xy. One thing I do want to note is we said that if we do the transformations correctly, that the transformed stresses always equal the original stresses. Well, the principal stresses are just transformed stresses, just special transformed stresses. So we can just say that sigma x is going to equal, that sigma xt for the maximum shear stress is just going to be when sigma x plus sigma y is equal to sigma x plus sigma y divided by 2. Which another way of saying this is just the average stress. All right. So using the problem up above, let's find theta s and then what tau max is going to equal. So I'll let you guys do that for a few minutes. And then I didn't actually make a get out of jail for you guys, but that doesn't mean you're getting away from it. It just means I'm writing it on the whiteboard today. And I will have to take a picture of it beforehand to then show you guys. Or I'll write it up and then I'll put it into like a nice PDF document for you guys to have. Nicole's looking at me like she wants to kill me.
I just love that you can't exceed.
No, you guys need the practice,
Not.
especially with statically indeterminate numbers. Yeah.
Which was the formula for tau max?
For tau max, there is no equation.
Wouldn't it just be 0?
What?
Would it just be 0?
Not quite, no. It can't be 0 because the maximum shear, the applied shear stress was 2 KSF. It's only 0 for when we have a principal stress plane. I just want to know what you guys get for the principal shear stress. Yeah.
Negative 22.5.
That was for the principal. I meant max, what for the shear plane. The maximum shear plane.
No.
Sorry. Yeah, to determine the maximum shear stress, just remember our 3 equations that you guys learned today. It would be using the transformed shear stress equation, just using theta s as the angle, which you guys should calculate theta s as 2 different values. Who here has got the angle? You got the angle, Nicole? Or the angles? Negative what?
37.8.
Negative 37.98. No.
Are we using the stuff from the last one?
Yes, 1, 2, and 3.
And we're using the half tan inverse equation?
Yes.
Can we put it
I think so. Who here got that also? What are you using for sigma x and sigma y?
3 and then negative 1?
I get negative 22.5.
Yeah, maybe I just plugged it
That's
in.
what I get.
Yeah. Though it's weird because I'm wondering if I have the equation wrong. I think this equation is supposed to be negative because your your maximum stress angles should be positive 22.5 degrees and negative 67.5 degrees.
How did you get the negative 67?
That's what I did when I did the plus or minus 45.
Yeah.
The two that I got.
Yeah.
When I did the half inverse tan, then I got negative 20.
Yeah, I think it's supposed to be a negative sign at the front.
You just added 45 degrees. So that's
Subtracted 45 because negative 22.5
Oh, yeah.
minus 45.
I
Yeah.
forgot there was that extra part.
Mm-hmm. Yeah, so I think there's supposed to be a negative here. I'm going to look into that further because my notes don't show it, but yeah, the plus minus 45 is correct. I know that for sure. And then for the maximum shear stresses, we just use our tau x y t equation, but we set theta equal to theta s for both situations. So if you use negative 22.5, you should get the following. Negative, what was the equation? Sigma x is 3 minus negative 1 divided by 2 sine 2 times 22.5 degrees plus negative 2 cosine of 2 times 22.5 degrees. What do you guys get for this, for the shear stress? Yeah, it is negative. It's supposed to have a negative, yeah. So, let me make that correction in my hand notes. There we go. Yeah, so the equation as shown for theta s is correct then. What'd you guys get for tau max?
For that one,
Yeah,
negative 2.83.
negative 2.83 KSF. Now, if we had set this instead of 22.5 to negative 67.5 degrees, what we would have gotten was positive 2.83 KSF. So it's the same value, just different signs, which means that the maximum shear stress is equal to 2.83 KSF. Now with these corresponding values, what are sigma xt and sigma yt equal to? Who here did that? If you plug them into that really long equation, you should get the same answer as a really short equation that I showed you guys. Get it, Michael?
I don't know. Are we supposed to use the average stress one that we just did? That's the one?
That's a trick. That is the answer. But if you use the transformation equations, you'll get the same thing. I want somebody to do it with the transformation method, also to show that it works. Who did it using the transformation equations?
Is it not? Didn't you do this?
Sigma xt and sigma yt. Well, for the shear stress, the thing is, there are basically an infinite number of possible stress planes. So there's one stress per plane. So for this case, we are considering theta equal to theta s, which is the normal stresses on our little block for when that maximum shear stress is occurring. Previously, we had did it for when we had a principal stress and no shear stress was occurring. That's what was the definition of the principal stresses. Now we are trying to figure out what sigma xt and sigma yt are for when the shear stress is maximum, not zero.
With the positive 22.5.
You can use positive 22.5 or negative 67.5. They both should get you the same answer.
So it wouldn't be the same as the last one we did, we would just flip the sign? If you use negative for the last one we did?
22.5.
Say that again?
No, don't worry about it. I'll figure out what she's saying now.
You would use either 22.5 or negative 67.5 in the equations instead of just negative
But it
22.5.
wouldn't be the same answers as we did last time?
No. You should get different answers. Yeah, so sigma xt is not going to be like 3.83. Sigma yt is not going to be negative 1.83. Matter of fact, sigma xt and sigma yt should technically equal the same thing if you did it right. Next class is going to make a lot more sense, I think, with explaining all of these. Because it's going to show you guys how to plot everything in a circle. Christian knows what I'm talking about, right? You am I right?
Right.
Yeah, I showed him earlier. Say that again?
Both would be equal to 1.
Yeah, who gets one KSF? Why is no one speaking up?
Gotta be stressing, bro.
Really quickly, who doesn't get one KSF? You don't? How did you do it? Did you use the stress transformation equations?
I'm kind of confused, so I
Okay. Well, here's how we would get to that. So you would use sigma x, the sigma xt equation. So you have sigma x, which was 3, minus negative 1, plus negative 1, divided by 2, plus 3 minus negative 1, divided by 2, times cosine of 2 times 22.5 degrees, plus negative 2 sine of 2 times 22.5 degrees. Now you can replace these also with 67.5 degrees, negative 67.5 degrees. That's a big difference. And what you should get plugging this in is 1 KSF. Let me just grab all of this. Just move that closer. And then if you did the same thing for sigma YT, if you recall, this equation is just the same as sigma XT, just instead it has negative signs. And again, it's going to equal 1 KSF. Does that make sense? All right. Another way of doing it is by using these expressions above. So both methods should work. You can take the average of the normal stresses, or you can use the stress transformation equations.
If it was an exam, would you care if we used them?
Not at all. Matter of fact, next class, actually, I really push on you guys understanding that the average stress is a coordinate location associated with the maximum shear stress. Yeah. So I'll show you guys how to draw the circles. It'll be nice and easy. You can basically solve for any stress state plane within a matter of 5 minutes instead of having to plug and chug the equations over and over and over again. The only thing you can't get is really the principal stress, is the principal angles. Those you need to use the equations for unless you draw the thing to scale and have a really good protractor that can measure to like very small angles. In which case then you would need to draw your circles neat, which I expect you guys to do. Also, I'll mention it next class. I was gonna say, don't use software to draw these circles. All right, I'm expecting them by hand if you're drawing them. All right. So, if you draw it by hand,
Whoever makes the pretty circle.
you can draw it in AutoCAD if you want. All right. I just don't want you guys going on a website and just plugging in the stresses and then having a result pop out. That's what I don't want. You guys can draw out the circles and draw out all of the symbols in like AutoCAD or something like that. I'm perfectly fine with that.